Hi, welcome to our lecture number 11. The topic today is the self-gravitating Klein-Gordon field. So what we did in the previous lecture, lecture 10, was that we studied the Klein-Gordon field and we studied the non-relativistic limit of the Klein-Gordon field on a curved spacetime. So we were asking if we have matter, quantum matter that we can describe relativistically by the Klein-Gordon equation, and we have this matter on a spacetime with a generic curvature. What is the Schrödinger equation? What is the non-relativistic Schrödinger equation with a gravitational potential that follows from that? And what are the relativistic corrections to this? So this was the previous lecture, the question, how does quantum matter behave in a given external spacetime? Now today we want to look at a slightly different question, namely the question, what is the spacetime of quantum matter itself? So, and we look again at this model of having a Klein-Gordon field in a curved spacetime, but now instead of giving the spacetime structure externally, we want to try to understand how does this Klein-Gordon field act as a source of spacetime curvature. So what is the spacetime curvature that comes from this Klein-Gordon field? And in order to do this, we look back at what we had before already, the minimal coupling principle. So we remind ourselves that if we want to couple a matter field, like the Klein-Gordon field here, to Einstein's equations for gravity, then the usual prescription is that of minimal coupling, which we described as having 4 different steps. So the first one was that we need a Poincaré invariant formulation of the field we have in mind. So this would be our Klein-Gordon equation. The second step would then be to find a general relativistic version of this by replacing the flat metric by the curved spacetime metric and partial derivatives by covariant derivatives. Okay. And these 2 steps are essentially what we did in the previous lecture. So this was the content of lecture 10. But now if we want to really solve Einstein's equations, we need to go beyond that. So we need to ask, what is the stress-energy tensor that belongs to this field? And as the final step, we want to solve Einstein's equations for this stress-energy tensor derived from this field to get a solution for our metric. So So the solution of Einstein's equations gives us, through the Einstein tensor, gives us a solution for spacetime. And this is essentially what we want to do today. So we make a similar approach. As previously. We do, as a first step, we do exactly what we did in the last lecture. Except that for simplicity, we will now focus on a spherically symmetric space-time. So the results in principle that we will derive would also apply to non-symmetric situation with slight modifications. But to keep the calculations as simple as we can, we now only look at the situation of a spherically symmetric space-time metric. So the ansatz we make for our metric tensor is that we have a time-time component that we write as e to the as e to the 2a, and a RR component that we write as e to the 2b. This is just a notation with the exponential function. I could also just write a function here without taking the exponential, but this makes it a bit easier to handle the derivatives of these space-symmetric elements, as we will see later. So I have a spherically symmetric situation, so I have a t and an r coordinate, as in the Schwarzschild metric, and then the spherical symmetry is just expressed by the fact that the other components are simply r squared d theta squared plus sine squared theta d phi. So this is the metric we're having as an ansatz now, and again we can, as before, we can do the same as we did in the last lecture. We can now expand the coefficients. So a and b here are supposed to be functions of r and t, of our coordinates, and we can expand. So we could expand those exponentials. So e to the a. For example, is a power series in powers of 1 over the speed of light with coefficients which I call an. So those depend on t and r. Where the A0 coefficients is unity. So in the non-relativistic limit, I just get ones here, and I get the flat space-time metric. Okay, the same I do for e to the power b with coefficients bn. And we can now do exactly the same procedure that we did in the previous lecture. We can actually immediately apply the result from the last lecture, just identifying this metric with the general case we considered in the previous lecture. And we don't care about those relativistic corrections that we derived last time. What we care is just the lowest order equation that we got, which was the Schrödinger equation with a Newtonian potential. And this will follow here in exactly the same way. So we will find from solving the Klein-Gordon equation, or from taking the non-relativistic limit of the Klein-Gordon equation in this curved spacetime, we find the Schrödinger equation for our coefficient psi 0. So we make the same ansatz for our wave function psi, or for our field phi. We write the Klein-Gordon field. Again, as in the previous lecture, we write the Klein-Gordon field as a power series with this exponential prefactor, e to the I s, plus or times power series where we have these coefficients psi I at different orders in 1 over c. And yeah, we find the lowest order contribution is just our non-relativistic wave function that solves the Schrödinger equation. IH bar psi dot equals minus h bar squared divided by 2n, Laplace operator. and then we have a Newtonian potential plus n phi acting on psi 0. So this is just what we did in the previous lecture. And now we want to, however, look at this phi, and this phi is now not something. So previously we had this phi directly following from our metric. So the phi was basically just the 0, 0 component, the 0, 0 component of our metric, if we linearize it. Now this phi is something that should follow dynamically from solving Einstein's equations for this field. So in order to do this, we need to look at both sides of the Einstein equations. We need to look at the Einstein tensor, the left-hand side, which you remember is the curvature tensor, the Riemann tensor. Sorry, no, the Ricci tensor R mu nu. Minus 1/2 g mu nu times the Ricci scalar R. So this is the left-hand side of Einstein's equations, which we need to look at, and then we have the right-hand side, which is 8 pi g divided by c squared times the stress energy tensor T mu nu. So we need to find the components of the stress energy tensor for our Klein-Gordon field, and we need to find the components of our Einstein tensor. And both of those we want to also expand order by order in powers of 1 over c. Oh, and sorry, I wrote c squared here. This, of course, has to be c to the power 4 in Einstein's equations. So yes, so let us have a look at those equations. So yes, let us look at the Einstein tensor first, and we will find that there are 5 non-zero components. So all the other components will be 0 for this symmetric situation that we have, and the 5 non-zero ones are the ones that are given here: the TT, RR, TR, theta, theta, and phi, phi components, which you can derive. So you would need to, from the metric approach that is given, you would need to calculate the Christoffel symbols. Once you have those, you can calculate the components of the Riemann tensor and then the Ricci tensor and Ricci scalar, and you can get the Einstein equations. So this is quite tedious but straightforward, and you end up with those 5 expressions in terms of these functions a and b that we have in our ansatz for the Einstein tensor. So this is G. So the stress energy tensor we can generally find from the Lagrange density, and it is given as in the notation we're using. So in the metric convention we have, it is given as -2 square root of minus the determinant of the metric, and then the variation of the Lagrange density by the metric components G mu nu. So now we need the Lagrange density for our Klein-Gordon field, and this is minus h bar squared divided by 2m, and then we have second derivatives d lambda phi star. So this would be for a complex Klein-Gordon field, but in principle it also applies for a real valued one. MC squared divided by h bar squared times the absolute value of phi squared, square root minus g. Okay. This square root minus g is a bit a matter of convention where you put it, and you have to be careful. So it's important for what we're doing in order to derive the Einstein tensor. It's important that we have the right prefactors. So those constants that appear here in front, for our purpose, are actually quite relevant. So if you will look into a quantum field theory textbook, for example, those are usually not even mentioned, because first of all, if you derive the Euler-Lagrange equations from this Lagrangian, then the prefactors do not matter. You can write whatever you want in front of it. Also for the stress-energy tensor in quantum field theory, the global prefactor usually doesn't matter, but for defining the right stress-energy tensor in general relativity, they are important. And then you have the additional problem that you usually have find the whole thing in units where h bar and c equals 1. So tracing back where the correct factors of h bar and c are is usually quite tedious. But so this is the correct form of the Lagrangian for the Klein-Gordon field. And now if we insert this in our T mu nu, and we do this variation, then we find that T mu nu is h bar squared divided by 2m. d mu phi star plus the complex conjugate of this minus g mu nu, and now there's a scalar expression d lambda phi star plus, this is basically just the Lagrange density again here, plus m squared c squared divided by h bar squared phi squared. Okay, so this is the stress energy tensor, and now we can again calculate the non-vanishing components of those, and that's exactly the same 5 that we had for the Einstein tensor. So we have the TT, RR, TR, theta, theta, and phi, phi components expressed in terms of those functions a and b and our field phi. So with this, now we do the same as we did before. What we did for the Klein-Gordon equation, we now do for the Einstein equation, namely we look at the Einstein equation order for order in 1 over c. So we start at the lowest order. So I made us a space at the board here, and we have to start at the lowest order, n equals 0. So what we do now is, it's actually, again, this is a quite tedious endeavor if we really wanted to do that in detail. So what we would have to do now is we need to expand these functions, e to a, e to b, and we need to insert the power series both in our function here for t, tt, for example, and then also for g. So what you see here is that that for the stress energy tensor TTT, we have a term that's order c to the power 4 as the leading order term. But remember that the stress energy tensor in Einstein's equations gets divided by c to the power 4. So this is actually a power of order 1 term at the lowest order. So the TT component contributes in the stress energy tensor at order c to the power of 0. And on the other hand, we have the Einstein tensor, and there you see you have the highest order contribution will be of the order c squared. So we can guess what happens, and you would now need to insert the power series and for e to the a and e to the b, and and for b prime. And what you find if you do this, if you insert all of that, is that you get only a contribution from GTT. So the stress energy tensor will give us a 0 contribution, and the equation that we end up with is we can write as RB1 prime equals 0. B1 plus RB1 prime equals 0. And so this is not immediately obvious from this equation. You would need to really write it down with inserting this ansatz to see this. But you can just believe me the solution. And if you look at the other components here, then you see that there is no c squared term. So all the others will not give any contribution, or will just be trivially satisfied. So will give us 0 equals 0 at the same order in 1 over c. So now we can go to the next higher order, which would be n equals 1. And again, we get at n equals 1, we get no contribution. Excuse me, we get no contributions from the other components. We just get a non-trivial contribution from the TT component. And the contribution we get from the Einstein tensor, we can write as 2 divided by r squared (3/2) b1 squared plus rb2 prime. And again, you can roughly guess the structure. So you see that the 1 over r squared obviously comes from the 1 over r squared appearing here and here, and that the b coefficients come out of this exponential. But you would need to insert the power series to see this in detail. And then at the same order, this is where for the first time we get a contribution. Contribution from the stress energy tensor 2 at the lowest order, and this at the lowest order just gives us 8 pi g, because remember we have 8 pi g divided by c to the power 4 in Einstein's equations. And now we have an n here too, and the e to the 2a half just gives us a unity, and then what we have is psi 0 squared here for the from the Klein-Gordon field, for which we also have to insert the power series, of course. So this is the equation at n equals 1. And again, this is the only non-trivial equation we get. All the other components still just give us 0 for both the stress energy tensor and the Einstein tensor. So we can go to the next order, n equals 2. And at this order, again, we find an equation from the TT component, which now looks the following way. Again, write this as 2 divided by r squared. Minus 4 b1 cubed minus 3r b1 b2 prime plus rb3 prime. And on the right hand side we have 8 pi gm again. But now we get a higher order term. Again, we only get the contribution still from the first term in the stress energy tensor. But now this has phi 0 and phi 1 terms coming together to give us an expression at this order. So what we have here is psi 1, psi 0 star plus the complex conjugate and now for the other components, yeah, so for the other components, we find as a result from from RR or theta theta. So if you look at the RR component, for example, at this order, you will get a B1 term here. So this exponential is basically 1 plus e to the 2b, and then you have the power series for b. So the 1 over r squared term here cancels. And for a, the spatial derivatives will also not contribute at the lowest order. So that's where the B1 comes in, and then the stress energy tensor for the RR component will yield 0. Again, because the lowest order here is c squared divided by c to the 4th. And so with this result, so we find B1 equals 0 from this one, and the same is actually true also for the theta theta equation. If you look at this, the TR component will give us B1 prime equals 0, but this is already trivially satisfied if B1 equals 0. And we can, and with this B1 equals 0, now we also trivially satisfy the equations at order n equals 0, and we can insert this here and here to simplify those equations. So what we end up with now, after having this order n equals 2, are the following. The following two equations. We have RB2 prime equals, so we divide by this 2 and multiply with this r squared, so then we have 4 pi gm r squared psi 0 squared. And essentially the same type of equation for B3 yes, and now again, now we can go to the next order, n equals 3, and I don't give you the equation at the board. I just show it to you in the script. So for n equals 3, we find this result. We find a slightly longer equation that contains now also a at the first time, an a coefficient. And again, we find equations for the RR, theta theta, and TR components. And now, if we put all of this together, then first of all, it helps to introduce the probability current. So this is first just, you can see this as just a definition, but it's also the conserved probability current that follows from the Schrödinger equation. So remember, we have already solved we've already taken the non-relativistic limit of the Klein-Gordon equation and gotten the Schrödinger equation with the gravitational potential. What we're trying to do now is finding the exact form of this gravitational potential. But the potential does not play a role in the probability current. You can derive the probability current from the Schrödinger equation regardless of what the exact form of this potential is. And you will find that this probability current, as is usual for the Schrödinger equation, will satisfy the continuity equation. So the divergence of J is a vector. Plus the time derivative of the absolute value squared is conserved, so this equals 0. Where you have to remember, so we are in a spherically symmetric situation. That's why we find a scalar J here, and the gradient in spherically symmetric coordinates is simply J prime, so the derivative by R plus 2 divided by Rj. Okay. So this is the definition of the divergence. Sorry, and yeah, with this J satisfies the continuity equation, and now we can use this to simplify the equations that we have. So the first equation that we find, which comes out of the RR component. Switch back here again, and so at n equals 3, we find B2 equals RA2 prime for the RR component, and this we can write as B2 equals R5 prime with the potential appearing in our Schrödinger equation. So remember that the potential phi that appears in the Schrödinger equation is simply the A2 component. So A2 we can identify with phi, at any time. That's what we did in the previous lecture. So we have this equation, B2 equals R phi prime. Then we find from the order n equals 2 equation. So at order n equals 2, we found this equation, R B2 prime. So that's the second equation we have. And finally, again at order n equals 3, we find an equation for B2 dot, this one, which comes out of the theta component, of the TR component. And this equation that follows from the TR component we can now express in terms of the probability current. And we find B2 dot equals minus 4 pi GMR J. Okay, so this system of 3 equations is now what we are looking at. So that's not all the equations that we have found. We also had at order n equals 2, we found that now we have this equation 1120 but this is an equation for B3 that also depends on psi1, so of the first order correction of our field. So this is something that is beyond what we are looking at now. So this will somehow give us constraints then on the higher order corrections, so on the relativistic corrections to our wave function, and on the higher order corrections of our metric. So for solving the system which we have at the board, this equation for B3 is not important. And the same is true for this equation, 1121, the really long one, is also an equation that depends on B4 and the fields psi1 and psi2. So this will somehow constrain those higher order terms. And those are all the equations that we had. So we have this system of 3 equations plus these 2 equations that give us further constraints for the higher order terms, which we would need only if we would go beyond this and go to really terms of higher order. Now what we can do with this is first that we can insert, so we have an equation for B2 here, and we have an equation for the derivative of B2 here. So we can combine those two into a second order equation, just inserting this B2 here. And we find from this effectively that we get the Poisson equation. So we get from the first two, we get 4 pi GM so 0 squared equals, and you will find that what you have on the other side is just the Laplacian of phi in spherical coordinates. So we find that psi 0 absolute value squared solves the Poisson equation. And now we have one equation left, this here with B2 dot. So yeah, I will just walk you through the steps, what we do with this third equation here with the lecture notes. So first of all, what we do is we can integrate the equation for B2 prime. So integrating equation 1126, let me go back. So this equation we can integrate. So we end up with this integral expression here. So B2 is simply an integral of psi 0 absolute value squared. Now we take the time derivative of this expression here, which gives us a time derivative of psi 0 absolute value squared. And this we can now, with the continuity equation, we can express this time derivative of the wave function squared by the divergence of the probability current in this way, where we already we also did the coordinate replacement here. So we replaced this r coordinate by a dimensionless coordinate x, so integrating from 0 to 1 of this x. And this we can actually write, so together with this 4 pi here, right? So this we can interpret this as an integral in spherical coordinates for a spherically symmetric function, which we can rewrite now as a volume integral. So this is just this volume integral of the divergence of J. So if this is a spherically symmetric function, after evaluating the theta and phi integration, we would just get this factor 4 pi and this one-dimensional integral over R here. Yes, so we have this volume integral of the divergence, which now, using Gauss' theorem, we can express as an integral over the boundary of the function J. And since J is a constant on this boundary, this is simply the following expression. It's minus 4 pi g mr j. And now if you look at this, b2 dot equals minus 4 pi g mr j, then you will see that we just derived exactly equation 1127. So this third equation, and now let me go back to the board. So this third equation already follows directly from the other two together with the continuity equation. So we can actually get rid of this and just add the knowledge of the continuity equation to our system. Or since we already expressed those two in terms of this one equation, we can say that the system we found, or the solution of the Einstein equation to this order, is equivalent to this solution of the Poisson equation together with the continuity equation for probability current. So this is our result. And now we can go one step further. We go one step further and we integrate this Poisson equation. And then we can, after integrating this equation, we can plug this potential phi into our Schrödinger equation as we want to. So the Schrödinger equation we find is, again, remember we have a spherically symmetric situation. So IH bar phi dot. yeah, so I assume now that we did this in a general case. Remember, the derivation, strictly speaking, was just for a spherically symmetric situation, but the result would be the same in a non-spherical situation. So the Schrödinger equation we would get in a general case would be minus h bar squared divided by 2m Laplace. And now we have the potential that we just derived, the potential that solves this Poisson equation. So after integrating this, we get minus gm squared. And then we have an integral 3r prime. And now the wave function at t and r prime, absolute value squared, divided by the distance r prime. Times psi. Okay, so this is this is just the Coulomb potential integrated. And what you have here essentially is now, so first of all, this is a nonlinear equation. So you see that that the wave function doesn't just enter here, so it's not just an operator acting on the wave function, but this potential that enters the Schrödinger equation here actually depends on the wave function. So through this becomes a nonlinear Schrödinger equation. And the way this behaves, which is much easier to see with this Poisson equation, is you have here the wave function, or the probability density that comes from the wave function, acts like a source of the Newtonian gravitational field. So you can think of it as if you have a wave function that evolves somehow according to the Schrödinger equation, but the probability density, psi squared, from this wave function, you can also interpret now as a mass density, so the total mass m of the particle is smeared out with the probability of this wave function, and acts like a Newtonian mass distribution. And the particle now sees the potential that belongs to this mass distribution. And so this equation is often called the Schrödinger-Newton equation. And I will you often abbreviate it just with Sn. Schrödinger, obviously, because it's the Schrödinger equation, Newton because it contains Newtonian gravity in this nonlinear way. And we want to continue now and discuss some properties of this equation. So the first remark is that that this equation actually falls into a more general class of equations, which are called Hartree equations. And those have the general form IH bar psi dot equals minus h bar squared divided by 2m Laplace. We can have a linear potential V, just any linear potential, just does not appear here, but we could simply just add any linear potential to this equation. If we have, for example, not just our Klein-Gordon field, but we also have some external electromagnetic field or something. And we can write then this nonlinear term as a convolution of some function phi with the wave function absolute value squared. And so just to remind you, or if you haven't seen this notation before, the convolution of two functions u star v of x is defined as the integral u of how do I call it here? U of x minus y, v of y integrated over y. Okay. And for Schrödinger-Newton, so the Schrödinger-Newton equation here is the special case where phi here is the Newtonian is the Coulomb potential is minus gm squared divided by absolute value of x. Okay. So for this choice of phi, we get the Schrödinger-Newton equation if we put v equals 0. But we could get more general expressions of this Hartree equation by having different functions here for phi. This Hartree equation can be derived from a Lagrange density. We need the following one. So this is the Lagrange density from which this Hartree equation follows. The first two terms are just the Lagrange density for the usual Schrödinger equation, also with the potential here, and then the Lagrange term that gives us the nonlinear potential. And now, as for every field, we can look at the symmetries of this Lagrange density, and we can use Noether's theorem to have a look at conserved currents. So Noether's theorem says that if there is a transformation of our fields, an infinitesimal transformation, so psi goes to psi plus epsilon phi, and this transformation leaves the Lagrange density invariant up to divergence terms, which are allowed. So under this transformation, the Lagrange density goes to L plus something that we can write as a divergence term. Then there is a conserved current that belongs to this transformation, and this conserved current is given by lambda mu minus the variation of the Lagrange density by d mu psi times phi. So, and the fact that this is a conserved current means that the forward divergence at d mu j mu equals 0. And one symmetry we find for this Lagrange density, which you also find for the standard Schrödinger equation, is the invariance under phase transformations. So if psi of tx goes to a new psi, which is e to the I alpha divided by h bar with some base alpha times psi. Then we get the same Lagrange density, so there isn't even a lambda here, we just have L goes to L. So we can calculate the Noether current J. And we do this separately for the space and time coordinates. So the space coordinate J is just, we don't have a lambda. So what we have is minus the Lagrange density derived by the gradient of psi. And now our epsilon here is I divided by h bar. Sorry, our phi here is I divided by h bar, and alpha is our small parameter, we assume. So we get I divided by h bar psi. Plus, but we also have to take the derivative. So remember, if we have a complex field, so effectively we have two fields. We have psi and psi star. So we need to do this for every field. We need to do this for our psi and our psi star. So technically we have two transformations. Psi goes to psi plus epsilon psi, and psi star goes to psi star plus epsilon psi star. So we get a second term here for the complex conjugate, which is now plus dl by the plus psi star I divided by h bar. So the plus here because the complex conjugate will get a negative phase, right? So this transform for psi star means e to the minus I alpha divided by h bar. So this I divided by h bar is a minus I divided by h bar for psi star here. Psi star. And yes, and this you can now write, so if you look at the Lagrange density, which I now unfortunately already erased, if you take these derivatives, you see immediately that this is just the probability current. So IH bar divided by 2m psi gradient psi star minus psi star gradient psi. So this way we get the probability current and we get the continuity equation for the Schrödinger equation from Noether's theorem for the invariance of the Schrödinger equation, or the invariance of the Lagrange density under phase transformations. And now we can also look at the time component of this current, and we do the same. So we get the derivative by psi dot here and psi star dot here, and we find, if we take these derivatives of the Lagrange density, we find that what we get is simply absolute value squared of psi. So the Noether theorem, the invariance under phase transformations of the Schrödinger equation, tells us also that the probability density, the psi absolute value squared, is a conserved quantity. This is why the probability, the probability interpretation makes sense, because if we have a normalized wave function, then it will remain normalized. And so we find these properties for the standard Schrödinger equation, but we see that they follow in exactly the same way also for the Lagrange density for the Schrödinger-Newton equation now. So the Schrödinger-Newton equation has exactly the same property. It will conserve probabilities, and it will also still have the continuity equation for the probability current. So we can use it without worrying, just in the same way we use the Schrödinger equation, and interpret the wave function as a probability. So we can also look at the Galilean variants of this equation, and this you actually are supposed to do as an assignment. So you will find this on a Moodle page. There are a couple of steps that are given to guide you through this. But essentially, you're supposed to look at the transformation of this field and the Galilei transformations, and we will find that the Schrödinger-Newton equation is Galilei invariant, just as the regular Schrödinger equation, and the conserved currents will give us the conservation of the momentum expectation value, the angular momentum expectation values, and will give us basically the Ehrenfest theorem, so will tell us that the classical trajectory is a conserved quantity, so minus m expectation value x plus expectation value pt. So this expression is a conserved quantity, meaning that at any time the expectation values solve the classical equations of motion. A second thing you do in the assignment is that you have a look at a rescaling invariance that this Schrödinger-Newton equation has. And again, I just give you the result as an observation. So, and the result is the following. If we have a solution, so psi of Tx is a solution of the Schrödinger-Newton equation. And we make the following rescaling. So we do a mass rescaling with some factor mu. So we write the Schrödinger-Newton equation, but now instead of for the mass m, we write it for the mass mu times m. And at the same time, we scale the time parameter with mu to the power minus 5. And we rescale all spatial coordinates with u to the power minus 3. Then again we get a solution of the Schrödinger-Newton equation, but with a different norm. So the new solution is mu to the power 9/2, and then we have this scaling, so psi of mu to the 5t mu to the 3x. So you have to pay attention. You have to do the inverse transformation here in the coordinates. That's why there is a plus 5 and a plus 3 here. contrary to the forward scaling of the coordinates. So this function will again be a solution of the Schrödinger-Newton equation, but now with the mass mu times m. So once we have found this equation, we, as physicists, we want to ask, well, is there a way we can test this equation? Or first we ask, well, what does it actually describe? Remember, we started with the Klein-Gordon equation in a curved spacetime, and we coupled this Klein-Gordon field to the Einstein's equation. So what is this actually an equation for? Well, we used in the last lecture, we said, well, the Klein-Gordon equation, even though it's a classical Klein-Gordon field, we still understand it the way that the non-relativistic limit of this Klein-Gordon equation gives us the Schrödinger equation, so it describes quantum matter. So if you trust this procedure and say, well, we can extend this procedure also to this case of the self-gravitating field, then we can say, well, this is now the Schrödinger equation for matter if we want to take into account the gravitational field of this matter itself. But the assumption we're making here, and this is important to point out, and we will discuss this in the next lecture, the assumption we're making here is that we can still use general relativity and a classical curved spacetime. So we are in a semi-classical model where we treat spacetime classically, but want to understand how quantum matter behaves when it's living on this classical spacetime. So we understand this Schrödinger-Newton equation that we derived now as a model for quantum matter on a classical spacetime. And once we have that, we want to know, well, does this have anything to do with the reality that we observe in the world? So can we test this experimentally? Are there any effects that might be visible in a lab experiment? And so for this, we want to understand a bit better how this equation behaves. And I've already mentioned, basically you can intuitively understand this as if you have the wave function, you have a wave function of a particle, and now this wave function feels itself as if it was a mass distribution. So it feels a gravitational potential as if there was a mass distribution. So if you start with a wave packet, say we have just some Gauss distribution in space, then in standard quantum mechanics, this Gaussian distribution will just spread. That's what a Gaussian does. It just spreads out because of the Schrödinger equation, because of the uncertainty relation, basically. Now, if this wave packet is also a mass distribution, then you can imagine, well, there is now a mass that attracts the particle towards the center. So there will be an effect that kind of counteracts this free spreading. So you can imagine if I put enough mass in there, maybe it will somehow keep the whole wave packet together rather than spreading. So that's the question, is there an observable effect? And there is actually a very simple way to estimate the magnitude of this. And for this, we first look at the free Schrödinger equation. So the Schrödinger equation without the Schrödinger-Newton potential. And if you start with a Gaussian wave packet, then you can just write down the time evolution of this. So the general solution, analytic solution for a Gaussian wave packet is the following. So it's spherically symmetric. So it has some width that we call A. Square root pi times A. And then there is a time dependence of the normalization factor, 1 plus IH bar T divided by MA squared. This to the power minus 3/2. And then it's basically a Gaussian, so exponential minus R squared divided by 2a squared. So that's the initial width of the wave function. But now the width of the wave function changes. The spreading needs to be somehow in here, and the spreading is expressed again by the same factor, 1 plus I h bar t divided by ma squared. Okay, so this is the solution of the free Schrödinger equation. And now we can look at the radial probability density, which I call rho of TR. So rho of TR is just 4 pi r squared psi squared. So this is the probability density of finding the particle at distance r from the center without caring where on this sphere it is. And so this I can now express as 4r squared divided by square root pi a cubed. And then we find 1 plus h bar square t square divided by m square a to the 4th to the power minus 3/2. And the square of this exponential, so exponential minus r squared divided by a squared 1 plus h bar squared t squared divided by m squared a to the 4th. And now we can see, okay, where does this radial probability density have its maximum? So at which radius is the particle most likely to be? At which distance from the center? And if we do this, then we find that its maximum, which we call Rp, for P, is at a times square root 1 plus h bar squared t squared divided by m squared a to the 4th. So initially the maximum is at this width a. And so we associate this with the width of the wave packet, and then it grows in time. This is the spreading of the wave packet is expressed by this time dependent term here. And we can calculate the acceleration of the width of this wave function. So the second time derivative of this. And we can just express this again in terms of Rp. So if we take the time derivative here, we find h bar squared divided by m squared Rp cubed. So you could also understand this Rp as a solution of this differential equation. So basically, instead of looking at the whole wave function, we just look at the shell of maximum probability and see this shell as now accelerating with this acceleration. And now, as an approximation, we ask basically what is the gravitational force needed to cancel this acceleration initially at the width a. So we have an acceleration h bar squared divided by m squared a cubed. And now we want this to be compensated by the Newtonian gravitational acceleration, which is gm divided by the distance squared. So we put a squared here for the distance, because we assume somehow that the gravitational potential is in the center, and our particle is at this distance rp, so it's like a distance a away from our center. So the question is, when do those exactly compensate? And we can express this as m cubed a equals h bar squared divided by g. So this is just a constant, which we can also write as the Planck mass cubed times the Planck length. And we can give a numerical expression for this. So this is 1.7 times 10 to the minus 58 meters kilogram cubed. Okay, but basically we say, well, if the product of m cubed times the width of the wave function equals the Planck mass cubed times the Planck length, then roughly we would expect that that this self-gravitational force in the wave function compensates for the free spreading of the wave function. So this is nice, and now we can plug in some numbers. And one actually finds, if one looks at, so for example, if one looks at wave functions that are around 1 micrometer, 1 micrometer is not just a random number, it's basically the, if you look at experiments that have been done with large molecules, interferometry experiments with large molecules, I mentioned those types of experiments before in the lecture, then the wave functions you have in these experiments, or also the distance between the grids, are roughly of this order of micrometers. So if we have a micrometer, which is a realistic scale for current experiments, then one ends up with something that is of the order of 10 to the 9 atomic mass units, so the weight of 10 to the 9 hydrogen atoms. And the experiments that are done are actually done with up to 10,000. So there are like 5 orders of magnitude basically between the masses we need and the masses we have in experiments. So this doesn't sound like it's super hard to get there. I mean, of course, 5 orders of magnitude are 5 orders of magnitude, but in principle, like this doesn't sound like, it's not 20, 30 orders of magnitude away. It's not like needing to build a particle accelerator of the size of our solar system or something like this. This is something, with a bit of effort and a few decades of time, lab experiments should in principle get there. So there is, however, one problem with this. And I probably erased a bit too much now. So we can look at the time scale of this type of expansion too. So we can just say, in the same approximation, if we want to know how does the wave function spread in time, then we can Taylor expand this, of course, for short times. So this would be our initial RP. Rp dot 0 times t plus 1/2 times the second order derivative times t squared. So we've seen that there is no first order derivative, and the zeroth order is simply a for our wave function that we have. So we find a plus 1/2 h bar squared divided by m squared a cubed minus gm divided by a squared. Excuse me. T squared. And now we can ask what is the doubling time? What is the doubling time for this wave function? So after which time has our wave function spread to a size of 2a? And what we find from this is that this time t2 can be approximately given as something that's basically a squared m divided by h bar. And now if we put, so first of all, if we have some fixed value for a here, right, then the larger the mass is becomes, the larger the time becomes we need. So if we want to make our mass 5 orders of magnitude larger, keeping a at micrometers, we have the problem that we also need to wait 5 orders of magnitude longer before we have a significant spread of the wave function at all. So even the spread we would expect from the free Schrödinger equation will get slower and slower and will get harder to observe. And on the other hand, we have the problem that if we want to make the mass larger, we need, of course, we need a larger molecule, so we need something that physically has a larger size. It's not a point particle anymore in good approximation, but has a physical size. Whereas we also want to, in order to keep this time short, right, we want to keep the size a small. But of course, this a, if this a becomes smaller, if the wave function becomes smaller than our actual object, then we can probably not use the Schrödinger-Newton equation anymore. This was an equation for a point particle, and if we have a molecule and have a wave function that's much smaller, that is peak much smaller than the molecule itself, then this will simply not be a good approximation. So we will have to look into the details of this, and that is something we will do in the last lecture of the semester. So just as one remark, so if we have this time scale here, and what we could do in principle is we have this scaling law that we found earlier, that I gave to you earlier, that you will have a look at for the assignment. So we could, in principle, if we have a solution of the Schrödinger-Newton equation, we could in principle scale again. So we could scale the mass with a factor nu, and remember that the times scale with mu to the -5, and all lengths scale with mu to the -3. So if we want to, for example, so if we found a stationary solution, so if we found some combination of n cubed times a, where we don't have a spreading anymore, then we also will see the same behavior. So we will see this observable effect that the wave function doesn't spread anymore, also for the rescaled mass. Right? So we have a mu to the power 3 here, and and mu to the -3 here. So if we do this scaling with mu, we will basically still find the same significant behavior that we can distinguish in an experiment. But the problem is that the time scales with mu to the -5. Right? So if we go up with the mass, then we can go down with the time here. If we go down with the mass, we have to go up with the time here. So we need to go to large masses to get to short times. We get to significantly shorter times if we just go like some orders of magnitude up with the mass. But we run into this problem that the distances also get shorter. So and this means that we are in this regime where the wave function will be very small compared to the actual size of the object. So the Schrödinger-Newton equation for a single particle that we had will just not be a good approximation anymore. So we will need to study what happens in a situation where we have a molecule that is a large object and we have a wave function that is somehow narrowly peaked, and like the center of mass of this molecule has much less position uncertainty than the size of the object itself. So this we'll talk about in the last lecture. Next week we will talk about the meaning of this equation at all. So how much sense does it make to even talk about this possibility of gravity being classical with quantum matter on it? Or is there a need to quantize gravity? Which arguments do we have for quantizing gravity, and why should one take this model serious at all? So that's the outlook for the last two lectures. And with this, I say goodbye and see you again in 1 week.